Let us now go through a quick summary of this unit. We started by developing a little bit of a toolbox. We developed the Markov inequality that gives us an upper bound on the probability that the random variable takes a large value. In particular, when the random variable is non-negative, if it has a small expected value, then there is only a small probability that the random variable takes a large value. And then we developed the Chebyshev inequality, which is in the same spirit, but it actually makes use of the variance of the random variable. And it tells us that if the variance is small, then the probability that our random variable is far away from its mean, that probability is also small. We also introduced a new concept, a concept of convergence of random variables. This was the notion of convergence in probability. A sequence of random variables converges to some number a if the probability distribution of x gets concentrated in the vicinity of this number a. And there is a particular technical definition that captures this idea. Once we have this notion of convergence, then we can provide convergence results, and our main convergence result was the weak law of large numbers, which says that if you start with a sequence of independent identically distributed random variables, and with the technical condition that these have a finite variance, if we form the sample mean, which is the average of n samples of this particular random variable, they are all drawn from the same distribution, then the sample mean approaches, as n goes to infinity, the true mean, in the sense that the probability distribution of the sample mean gets concentrated arbitrarily close to the true mean. Then we presented the central limit theorem, which is perhaps the most important result in all of probability theory, and which gives us a lot more refined information compared to the weak law of large numbers. It tells us that if we take the sum of n independent identically distributed random variables, subtract the mean, divide by the standard deviation of the sum, so that this is a random variable with zero mean and unit variance, as n goes to infinity, the distribution of this quantity starts to approach a particular shape, and it's the shape of the standard normal. Strictly speaking, this is a statement about convergence of CDFs. On the other hand, the way we use this result is to just pretend that the sum of many IID random variables is a normal random variable, and then carry out calculations, calculate any probabilities that we may be interested in by just pretending that this is so. We also saw that we can get somewhat better numerical results. We can get more refined estimates in the discrete case, if we're dealing with integer random variables, by playing a little bit with how exactly we apply the central limit theorem to a particular situation. And then we had a very quick introduction into the framework of classical statistics. Classical statistics as opposed to Bayesian in the sense that the quantity that we're interested in is treated as an unknown constant, not as a random variable, so there's no probability distribution attached to this quantity. We still have a model for our observations, for our data, which is affected by that parameter, but it is just affected by that parameter. This is not a conditional distribution in the sense of Bayesian inference or of probability theory. Even though theta is not a random variable, there are still reasonable things that one can do to estimate unknown constants. For example, if the unknown constant is the mean value of a certain probability distribution, we can estimate theta as follows. Generate lots of samples from that distribution and take the average. And we saw that this is a nice estimator. For example, the mean squared error of this particular estimator goes to zero no matter what theta is. And this idea can be used more generally. Whenever we have an unknown constant which can be expressed as the expected value of some function of a random variable that we will get to observe, we can estimate that constant by generating independent samples of that random variable, call them xi. For each such sample, calculate the value of the function and then take the average. So this is an estimator which again will be consistent in the sense that as we get more and more data, the estimator is going to approach the true value of the parameter. However, point estimates are not enough. We also need to have some information about how accurate they are. And this led us to the notion of the confidence interval. We get the data, and based on the data, we construct an interval. Because the data are random variables, the endpoints of that interval, which depend on the data, will also be random. And this confidence interval will be said to be, let's say, a 95% confidence interval if it has this property. With probability 95%, it captures the true value of the unknown parameter. Of course, there's nothing special about 95%, except that this is the most common choice. But you could also form 99% confidence intervals if you wanted. In terms of the mechanics of how to construct such confidence intervals, typically you use the central limit theorem here. For example, this estimator is approximately normal when n is very large, and using that fact, you can form an interval around the estimator and choose the length of that interval so that it has exactly this property. Sometimes this calculation requires also to know the variance of the estimator. And if you do not have that variance available in some analytical form, you can still estimate that variance by using this estimation trick that we discussed earlier. You can form something of the type of a sample variance, that is an expression that looks like the variance except that it is calculated on the basis of the data, and use the estimated variance to construct your confidence intervals. Finally, if we're trying to estimate a constant, an unknown constant, that cannot be expressed readily as an expectation, there is still a general methodology for forming estimates, which is the maximum likelihood methodology. Namely, we ask the question, for the particular data that we have observed, what is the value of theta for which those data would be most likely? Maximum likelihood estimation has a little bit of the same flavor like maximum a posteriori probability estimation. It involves pretty much the same kind of calculations. In terms of calculations, it is just equivalent to maximum a posteriori probability estimation, where you assume a uniform prior over the thetas of interest. However, despite this formal resemblance, it's important to realize that conceptually they are very different. In one case, you ask what is the theta which is most likely. This is in the Bayesian setting, whereas here we ask which is the theta that makes my data most likely. In any case, this is just a glimpse into a huge field, the field of statistics, on which you are of course welcome to take further classes and dive deeper into that subject.